Are you a storm chaser?
I am a storm chaser, and I like to say...
Like the ones we see in the movies?
Like the ones you see in the movies, yes.
From the heart of The Ohio State University on the Oval, this is Voices of Excellence from the College of Arts and Sciences, with your host, David Staley. Voices focuses on the innovative work of arts and sciences faculty and staff, with departments as wide-ranging as art, astronomy, chemistry and biochemistry, physics, emergent materials, and mathematics and languages, among many others. The college always has something exciting happening. Join us to find out what's new now.
Joining me today in the ASC Marketing and Communications Studio is Jana Houser, Associate Professor in the Department of Geography at The Ohio State University College of the Arts and Sciences. She specializes in radar analysis of tornadoes and the supercell thunderstorms that commonly produce them by using state-of-the-art mobile radar observations. Dr. Houser, welcome to Voices.
Well, David, thank you so much. It's a pleasure being here, and I am thrilled.
As am I. And I know that you're going to be delivering a Science Sunday talk on the subject of tornadoes. Could you give us a little sneak preview of what you're going to be talking about?
Absolutely. So I won't give this away as a spoiler, as I am not 100% sure settled on everything, but I will be talking in some loose capacity about tornadoes, how they form, why they form, and also adding a little bit of climatology in there as well. So one of the big questions I almost always am getting these days is, what is the link between climate change and tornadoes? And most of the time that's led off by tornadoes are getting more intense, they're getting more frequent, right? And so then I address that question in this Science Sunday talk.
What are you going to say about that? Is climate change having an impact on
That is
tornadoes?
a great question. And actually the answer is we don't really know, but probably not, at least in the individual sense. So tornadoes are very difficult to extract from very localized, small-scale processes. So the climate system on a whole, in a global sense, is large. It's broad. You have large-scale changes in temperature distributions and precipitation distributions, and there are certain things that we can very clearly point out. The sea surface temperatures of the Gulf of Mexico are getting warmer.
Yes.
We know that. Scientifically, it's a fact. But the sort of breakdown is that tornadoes are very much dependent on these localized processes that are not climate related. And in fact, sometimes we can have tornadoes that are formed from situations where we have a terrain feature that happens to enhance certain environmental conditions. So as a result of that, we don't always know, even in an environment that is broadly speaking favorable to produce tornadoes, we don't always know if you have 13 storms in that environment, 4 of those storms produce tornadoes, but the other 9 don't, when hypothetically they should be in very similar conditions. So what is it about those 4 storms that did form tornadoes that is special? And that's an ongoing research question that we're still trying to delve into, and we don't really have the full answer to. But we're learning more and more that those differences are very small scale. They have to do with things like storms colliding with each other, things like the terrain lay of the land. So where are there rivers, where are there valleys, where are there mountains? Even perhaps things like friction, so surface roughness, and areas of forest in adjacent context to grasslands, perhaps. All of these small-scale things that aren't really directly linked to climate can, at the end of the day, affect whether or not a storm ends up producing tornadoes. So we can look at the large-scale environment, and we can say, in a broad sense, climate change is affecting the large-scale environment that may or may not be favorable for tornadoes in this way. But we still can't really isolate individual tornado events in the context of climate change.
So I want to be careful how I ask this then. You and meteorologists and those who study tornadoes, are you able to predict tornadoes?
The answer is sort of.
Sort of.
So a nice scientific hand-wavy answer.
And tornadoes versus, say, individual tornadoes. Maybe that's a distinction.
We know what we are looking at in the environment in order to say condition X, Y, and Z are being met. And as a result, the likelihood for tornado-producing storms is considerably elevated compared to if condition X and Y were here, but condition Z were not. So we are good at identifying these environments now. We understand that part. But when I am looking at a radar image of 5 storms back to back, and I am in the field trying to decide, like, oh, do I want to see a tornado, and am I going to go after storm 1, 2, 3, 4, or 5? I don't know, even sometimes 10 minutes in advance, which of those 5 storms will ultimately be the one to produce a tornado. Maybe they all will, maybe none of them will, maybe the middle one will, maybe it won't.
Because they're so localized, is that the fundamental reason?
That's exactly correct, because there are these small-scale dependencies on that formation process that we haven't extricated from the larger scale environmental.
Can you imagine a day when we will have that kind of predictive capacity?
I don't think so, quite frankly. I think what we're moving towards in terms of predictability and forecasting accuracy is more looking at high-resolution numerical models that produce individualized storms, which we're there. We can do that. We're still, again, working on some of the nuances. So, for example, in these high-resolution models, we don't represent turbulent processes particularly well because they're very small. So turbulence is basically the breakdown of larger scale wind patterns into very small little swirls and dissipation. So if you think about a situation where you're on campus, let's say, and the primary wind direction is out of the south, and you go behind a building and all of a sudden you notice the winds are out of the north. Why is that? Well, that's because the winds are encountering that building and swirling around and breaking down and becoming out of the north instead. So these processes occur on very, very small scales, much smaller. We're talking sometimes, centimeters in scale. So much smaller than what our weather models can actually resolve. And our best weather models that are used to predict and forecast storms have this sort of distance as about 3 kilometers in the square shape.
Does that make tornadoes different, say, from hurricanes? I've always had people say to me, I know with 2 days' notice that a hurricane's coming, whereas a tornado I might have 20 minutes, 30 minutes or so to prepare.
Yeah, if you're lucky, you have 20 or 30 minutes to prepare. So yes, they are very different entities. They're very different beasts. If you think about a hurricane, hurricanes last for days to weeks. Right. And we may not know exactly where those end up in terms of 2 days out, is it going to hit this city or is it going to hit the next city to the south? We can sort of say it's about in here, but we at least know a hurricane's coming, right? So we can make those preparations, we can make evacuations. For tornadoes, we can identify that environment once again, but that environment might be favorable over 5 states. So where within that 5-state area are we going to be most likely to see tornadoes? That's still a bit of a debate.
Are you able to, or are meteorologists able to discern moments when there might be one tornado versus multiple tornadoes, which we just saw that in Florida with the hurricane. There were 100 or so tornadoes that came with it. Do we have that kind of knowledge, or is it all of a piece of this unpredictability?
Yeah, again, we are good at the large-scale environment. So we know, for example, when we would expect a large-scale tornado outbreak because the environmental parameters over a relatively large area are going to be favorable to produce tornadoes. Similarly, we can identify slightly smaller risk areas where those parameters that are favorable overlap over a much smaller distance. The challenge that we sometimes have is what I would call rogue tornadoes, where you don't have...
That sounds terrifying.
Right? So you don't have the typical pre-existing conditions, and yet there's something that's slightly special about just this one storm. So nothing else is really a red flag for a forecaster in the morning, let's say. But then all of a sudden, you're seeing signs of rotation, and you're like, oh, what's happening here? And it just so happens, again, this gets back to that idea that the conditions are sometimes very isolated and localized. And so in these otherwise unfriendly conditions, maybe your tornado or your storm producing the tornado entered a river valley. That river valley is channeling wind that's parallel to it, And for the brief 10 minutes that that storm is crossing the river valley, those parameters are changed just enough to tip the scale, and all of a sudden you can produce tornadoes. And it doesn't do it beforehand, it doesn't do it afterhand, but just kind of right in that sweet spot.
Sounds like we need a lot of data, and we're never going to be able to get that fine-grained enough data.
And that's exactly why I said we're not really ever going to, I think, ultimately hit the nail on the head with tornadoes. Even when we understand formation mechanisms kind of down to a T, there's still this element of chaos. The atmosphere is chaotic, and we can't predict chaos.
Well, I'm interested to know about your current research, and I know you're using mobile radar observations to study tornadoes. Tell us more.
A mobile radar is basically an instrument that you mount on the back of a pickup truck and you drive it to the storms and you collect data with your instrument pointing at the storms. I have a history of going out with such instrumentation since I was an undergraduate. I did my undergraduate degree at Penn State University, and my very first field experience was going out with these radar trucks and collecting data on tornadoes in the field. And so what you do is you have this instrument that sends out energy. The energy hits the storm, it hits precipitation, and some of it returns to the radar. And from there, you can look at structural features of the storm. You can look at winds in the storm. We even now are capable of discerning differences between where there's hail versus where there's rain versus where there's snow. And so all of these things can kind of combine together to help us create a better understanding and start filling in puzzle pieces of how tornadoes form, especially as we're looking across time and seeing the storm before tornado formation, during tornado formation, and after tornado formation. If we can get a nice long data set that shows us that continuum, we can really start to pull out information about the storm that compares it from the before tornado to the during formation process to the after as well.
So, and I'll ask two questions, but it's actually the same question. How close do you or your technology have to be to a tornado? And I guess I'm also asking, how close have you been to a tornado?
So these instruments, these mobile radars, are relatively large and they're very expensive. So we operate within what we would consider, to us as skilled experts, a safe operating distance, which is at least a mile away. So we don't want to be really up in the tornadoes business because we don't want to be hit by flying debris. And in all honesty, sometimes the scientific mission at hand requires us to take a little bit of a step back so we can get a larger scale perspective of what's happening, not just immediately within the tornado, but within the storm itself, kind of surrounding the tornado and the environment surrounding that too. Oftentimes, it's just a matter of opportunity and luck and what is out there on the roads and where the storm is in comparison. Oftentimes we'll start a deployment and the storm is 15 miles away, and then we hope that we can stay in that same spot as a storm comes close to us, really close to us, but doesn't actually mow us over and then starts moving away from us. And that point, we basically undeploy and move on and kind of do a little leapfrog game with the storm, and we try to get ahead of it again and redeploy. Oftentimes throughout the course of a deployment, we start far away, the storm comes to us, and then once it passes us, we move.
What's the closest you've been to a tornado?
The closest I have been to a tornado has been, I would say, too close. One time in a radar truck where we were trying to outrun a different tornado, and then another tornado subsequently formed very close by. We were close enough to have leaves and sticks and shrapnel falling on us from out of the sky, at which point in time we stopped driving and turned our radar on and were like, wait a second, we are really close to a tornado. So that was probably a matter of a couple hundred yards. But interestingly, we didn't even see it. So it was a strong wind swirl, and there was just enough trees on the horizon, and I don't really even know what else, but we didn't actually see a funnel, we didn't see the debris, we just started getting rained on. So that was one time. And then another time without a radar truck, when I was out doing some filming for the movie Twisters, we basically drove through a tornado without intending to because it was entirely enshrouded in rain. And thank goodness it was a very weak tornado, so we got blown blown around a little bit. Again, not intentional, and there was very minimal visibility, but the rain was going pretty strong from the one direction, then all of a sudden it stopped, and then all of a sudden it blasted in from the other direction. It jostled the vehicle around a little bit. But, the winds were probably maybe 70 miles per hour or so it was not a very strong tornado.
You just mentioned the movie Twisters, and I was going to ask, are you a storm chaser? But then I thought, maybe that would be impolite to ask. Are you a storm chaser?
I am a storm chaser, and I like to say...
Like the ones we see in the movies?
Like the ones you see in the movies, yes.
Okay.
So I like to say that storm chasers have different flavors. So there's the scientific flavor. So I was basically describing already what storm chasing from the scientific perspective is like. You go out with instrumentation, you try to get yourself kind of close to a tornado, you collect scientific data to try to answer questions. Then there's this other category where I would sort of also put myself, which is a person who is excited about tornadoes, who wants to see tornadoes, and not necessarily just for the science purpose, but to go out and just visually see them and experience them. So I have done that without scientific equipment as well. And then there's this third category that I don't fall into, which is more like what you see in the movie, Tyler and his crew, out there with YouTube and trying to get as close as they possibly can, shooting rockets into things, etc. So I'm not selling my video. I'm not trying to make money off of storm chasing, but I do it as an exciting pastime.
Well, you said you were involved in the movie Twisters. What was your role?
I worked with a film crew. I have a history with an IMAX cinematographer named Sean Casey. We go way back to that very first field experience I talked about when I was an undergraduate student at Penn State. He designed a vehicle to penetrate tornadoes. So basically got a truck chassis, stripped it out, put a bunch of iron plates on it, reinforced the windshield with bulletproof glass, put a turret on the top for his camera, and was trying to essentially drive in and video what it was like to be inside a tornado. Now, our mission for Twisters was not that, but we talked to each other. So about 2 years ago, a little less than 2 years ago, I was thinking about Sean, and I just happened to reach out to him. We stay in periodic communication. Sometimes it'll be years between times we talk. I'll always ask him if he's going into the field, if I'm going into the field. So I was asking him, like, hey, are you planning on going out and storm chasing this year? And this was the spring of 2023. And he said, yes, actually I am. And I was like, oh, well, that's exciting. What are you working on? And he said, well, I can't tell you what I'm working on, but I might need a meteorologist. And I said, oh, really? And it turns out that it was for Twisters, and it was before he could freely talk about being contracted to do this work. And eventually, shortly thereafter, he told me what it was, and I was like, yes, I will absolutely come and participate with you. So I served basically as the meteorologist to guide him and a colleague into the path of these storms, not explicitly trying to get run over by the tornado, but we were out to film B-roll and to get footage for the green screen in the background. So things that the actors can be superimposed upon. Dark skies, lots of cloud motion, blowing winds, things like that. So I chased storms for 3 weeks in the spring of 2023. And some of the footage that we shot did end up in the movie. So it's pretty cool.
Your mobile radar vehicle, how's it different from other such vehicles? I assume that this is sort of a next generation technology or something like that. What's different?
So the radar that I have gotten most of my data from is an instrument from the University of Oklahoma. And it is a rapid scanning radar, which makes it unique from most other radars. So most of the time when a radar is collecting data, even our best radars that are used for research purposes, it takes them about 2 minutes to scan the atmosphere and collect the information that we need. This radar, which is called Raxpol, is special because its antenna can spin very quickly, and it has a special configuration that allows it to collect data expressly, very quickly. And that allows it to collect the same data that would have been collected over that 2-minute increment. We can collect with Raxpol in about 20 seconds. Oh. So tornadoes are obviously a very fast moving and fast evolving phenomena. if you're looking at a time frame of 2 minutes, a lot can happen to a tornado in 2 minutes. So it's really important to get these high temporal resolution data so that we can start filling in the gaps of what's happening over that 2-minute time frame in a much better and clearer sense. So we're, again, starting to put puzzle pieces together and really understand the processes more rapidly. Moving into the future, I'm actually going to get my own radar that's even super cooler than the Raxpol is, and I'm excited to talk about that too.
Say a little more about it.
Okay, great. So thanks to The Ohio State University and a grant that was provided through OSU, I am in the process of procuring what is called a phased array dual polarization mobile radar. So that's a lot of science lingo in there. What I mean by that is it is not a conventional radar antenna. It collects data incredibly quickly. So the data that the other radar took 20 seconds to collect, this one can collect over about 5 seconds. Ooh. So it's, again, another temporal improvement in resolution. And then simultaneously, it sends out 2 types of energy waves. The one is oriented kind of like a snake, or if you can think about like 2 little girls holding a jump rope and swishing it back and forth really quickly, you have this wave that is basically like parallel to the ground. And then the other one is oriented like an ocean wave, so it has a vertical distribution in the waveform. And so by sending out both of these waves, we can get information about the precipitation a lot more effectively than we could using just one or the other type of waveform.
Now, I know that one of the conclusions of your research has to do with the formation of tornadoes, and it turns out tornadoes form from the ground. Why is this so important and significant?
Yeah, this is an incredibly important scientific, I'll call it re-emphasis, maybe not discovery, but we need to know where rotation comes from to feed tornadoes in the first place.
Starts in the sky, right?
Well, it turns out sort of. I'm saying that a lot, right? Sort of. That's part of the story. The full story is we have a broader scale rotation in the cloud that the storm itself is producing. And we need that broader rotation in the sky because what that does is it actually acts like a vacuum cleaner and it sucks air into it from below. But we also need to have rotation that's based at the ground, because if you have a vacuum that's sucking air in from below with no rotation, you never get a tornado. But you need to have that rotation present at the ground to begin with. So using this Raxpol radar that I've alluded to, we have learned that that very strong rotation is actually present at the ground first and then very quickly either translates upward with time or sometimes it actually simultaneously sucks together and you get kind of over the lowest couple hundred yards or so of the atmosphere, you get a simultaneous increase in the rotation, almost like a tube that suddenly gets pushed together, and everywhere you're sucking that tube in and it's spinning faster and faster.
This is why terrain matters.
That's exactly right, yes.
Did you discover this property?
Well, I didn't necessarily discover this in terms of the theory. The theory has been around for at least 50 years, since the 1960s. But my contribution, as well as one or two other individuals who were part of my research group, our contribution was to provide the observational evidence that supports this non-descending theory, aka tornadoes don't form in the cloud and move to the ground. I will add, the funnel cloud behaves differently. So for all of us observers who have ever gone storm chasing, and even for the average day person who is watching tornadoes on TV, you see the funnel cloud descend out of the cloud first, right, and then eventually sometimes get to the ground, sometimes it doesn't. But really, when you see that funnel cloud, many times there's already rotation that's tornado strength at the surface. We just can't see the whole visual because the air column itself, air is invisible.
Could I feel it if I were on the ground in that spot? Would I be able to feel it?
Yes, you absolutely would. You would feel wind blowing around like crazy. You would see leaves being picked up. You might even, if it's strong enough, you might even see roofs starting to wobble a little bit. And it happens quickly. Tornado formation happens on the order of a minute or sometimes even less. So that puts things into perspective when you're trying to give your weather person a little bit of a hard time saying, oh, I have a tornado warning, but no tornado ever happened. Really, we're trying to forecast in advance a process that's happening very, very quickly, and we don't oftentimes know the end result until we get to the end result. So we want to provide enough time for people to take action if a tornado does indeed end up forming, and we can recognize certain characteristics of storms that are capable of producing tornadoes. Now, whether or not they actually produce tornadoes ends up being still a little bit of a question mark.
So why do you study tornadoes? I mean, of all the meteorological phenomenon you can study, why did you settle on tornadoes?
We kind of joke in this field that we're genetically modified to want to do what we do. And this is pretty holistically true across meteorology as a full discipline. We collectively find ourselves being intrigued by various different weather phenomena from a very early age. So I was 7 years old, and my elementary school teacher, her name was Mrs. Ruth Rader in Pennsylvania. We did a unit in science class on the weather, and we talked about fog, and we talked about storms, and I was just totally intrigued by this. And I started watching the Weather Channel, and now I've got to date myself a little bit here. So this is like the late 1980s when the Weather Channel was still a scientific channel and a little bit less mainstream. And so there was a lot of really great information. And I would watch the Weather Channel like kids watched cartoons. There was also a really high impact event that occurred in the spring in April of 1991, where a series of very damaging and destructive tornadoes hit south central Kansas. And I was particularly impacted by the Andover, Kansas tornado of 1991. And that was really the first time I can remember seeing a tornado through the TV and seeing the catastrophic damage that was incurred. And for whatever reason, just this like juxtaposition between the violent ferocity of the winds and the damage that they can produce. And yet, when you look at tornadoes, they're graceful. There's an element of beauty to them. And this contrast was just very exciting and intriguing to me. So in fourth grade, I can clearly remember going to the library and trying to find like information on what you need to do to be a tornado chaser. And this is way before the internet and YouTube and all of that. And I found 3 little books and was so unsatisfied with what I found in those 3 little books. But I did a little school project on what do you want to be when you grow up. I made a diorama of a tornado, and I think I even put a little car in there, and, you know.
So you knew you wanted to be a storm chaser. You never went through a phase where you wanted to be like a TV weather person or anything like that? Al Roker, I don't know.
Right. Very initially, preliminarily. I don't know that I wanted to necessarily be that, but I can remember, again, probably as a 7-year-old kid, being on my parents' back porch, and my cousin, who was the same age as I am, we used to do this little play thing where we would go outside, and my dad had a thermometer and a little rain gauge, and she would pretend to operate a camera, and I would look at the thermometer and the rain gauge and look up at the sky and deliver this like brief little weather forecast thing, even from that early on. I was also the TV weather person in junior high school. When we had a journalism class in 9th grade, and so the weather was always sort of my thing to do. So I would make little notes, watch the Weather Channel in the morning, and then like translate the forecast that I thought was going to happen. So it was not necessarily a real career option for me, but I did do a little bit of exploration.
And I know you have music in your background as well. Say a little more about that.
Yeah, that's right. So music is some of my first memories. I've been playing the piano since I was in first grade, and also picked up the flute. And so I played the flute. Flute was more my primary instrument. So I did flute competitively through high school and participated in state bands. And I was really a band person with a little bit of emphasis of performance in there. I also sing. So in fact, my very first solo debut was singing when I was 3 years old in church. I made a little mess up at the end, and the audience giggled because I was so cute, and I was mortified because I was really sad because I messed it up, and it stuck with me all of these years later. I have a little piano composition that I wrote as a kid that was published in a piano magazine when I was 9 years old. So yeah, the music kind of runs deep.
But music never displaced storm chasing at any stage. You were not going to be a musician, right?
I thought briefly in high school about pursuing music education. I had some really fantastic experiences with my school band, and then that was followed by some not so fantastic experiences with a different band director. And I was very moved by the impact people make in the process of excitement over young students in music. Yeah. And I wanted to bring the love of music into other people's lives and other students' lives. So I briefly did consider doing music education for probably a year, like my junior year of high school, as I was kind of navigating the college scene and trying to figure out what I wanted to do. But I decided that music is something that I will always have. And if I went the way of being a meteorologist and decided it wasn't my thing, I could pretty easily pivot and go back to music. But the same cannot be said about the opposite direction. Calculus does not come easy to somebody who is 40 years old, who has been a musician their whole life and now is trying to reverse their tracks. So I ultimately followed my passion for weather and meteorology and pursued that in college and have never looked back.
Tell us what's next for your research.
So I mentioned the mobile radar that I'm in the process of procuring, and that's really the new, cool, exciting thing. I'm really super excited because there's nothing currently in the field like this instrument. It's really a one-of-a-kind thing. And what's really cool is that if we can place this instrument with another one that's very similar, and there is plans, in fact, the University of Oklahoma has a division of radar engineering specifically geared towards weather radar. So the Advanced Radar Research Center, or ARC, at the University of Oklahoma is in the process of developing their own version of this type of instrument. So I've already been in talks with a colleague of mine out there at OU. And if we can place both of these instruments simultaneously in the vicinity of a storm as it's producing a tornado, we can get incredible data that is going to help us really understand the origins of the rotation that goes into the tornadoes. So I mentioned, I'm going to backstep here a slight second. I mentioned that we need ground-based rotation. The question that we still have is, where does that ground-based rotation come from? And so we need to answer that question. There are multiple theories out there, and it could be that they all are correct in their own way, and maybe one storm produces that ground-based rotation a different way than another storm does. But we don't really have ground truth to confirm that. We have modeling studies which now have actually surpassed what we can do capably with observations. And we need to bring that observations back into the picture so that we know what our models are doing is what's actually happening in the real atmosphere too. So if we can get these two radars to simultaneously look at the storm, then we can generate trajectories that tell us where air is coming from, where it's going, and ultimately what the source of that rotation is. And that will be a really big advancement in our understanding of tornado formation.
Jana Houser, thank you.
Thank you so much. It's been my pleasure.
Voices of Excellence is produced and recorded at the Ohio State University College of Arts and Sciences Marketing and Communications Studio. More information about the podcast and our guests can be found at go.osu.edu/voices. Voices of Excellence is produced by Doug Dangler. I'm Jen Farmer.